Dear students, today let us discuss about some inorganic topic from module 2 about representative elements 1. So first let us discuss about the structure of aluminium chloride. This is a topic from boron family. We know that aluminium is having an electronic configuration of neon 3s2 3p1. Neon means it contains 10 electrons. So altogether there are 13 electrons in aluminium, 10 plus 2 plus 1. But in the case of chlorine, there are 17 electrons. From neon, there are 10 electrons and plus 2 plus 5. So there are 17 electrons in chlorine. So these 3 electrons from aluminium can form covalent bond with the chlorine atom. That means there are 3 electrons in aluminium, and then there are 5 electrons around chlorine atom in the outermost shell. 2 plus 2 plus 2 plus 1 electron. That 1 electron is used for forming covalent bond with aluminium. So there are 3 covalent bonds around aluminium atom. So altogether there are 6 electrons around aluminium atom. So it needs 2 more electrons in order to attain noble gas configuration of 8 electrons. So it can accept a pair of electrons from the neighboring AlCl3 unit. That means aluminium chloride exists as Al2Cl6 dimers in vapor phase around 400 degrees Celsius and in solution in nonpolar solvents like benzene. So usually aluminium chloride is having the formula AlCl3, but it can exist as dimer Al2Cl6 in the vapor phase around 400 degrees Celsius. And also when we use nonpolar solvents like benzene, it can exist as dimer Al2Cl6. This illustrates the tendency of aluminium to achieve a noble gas configuration by accepting an electron pair from chlorine. Each aluminium Al2Cl6 dimer contains 2 coordinate Cl-Al bonds in which a lone pair on chlorine belonging to one AlCl3 unit completes the octet of aluminium belonging to the second AlCl3 unit. This results in more or less distorted tetrahedral arrangement of chlorine atoms around each aluminium atom, which perhaps assumes a state of sp3 hybridization. So around aluminium atom there are 6 electrons, but it needs 2 more electrons in order to attain noble gas configuration. So it accepts a pair of electrons from the neighboring AlCl3 unit. There are 2 AlCl3 units in Al2Cl6 dimer. One is this AlCl3 unit, another one is this AlCl3 unit. So this aluminium atom can accept a pair of electrons from chlorine atom. There are 3 electron pairs in all the chlorine atoms, but when one electron pair from this chlorine atom coordinates to this aluminium atom, there are only 2 electron pairs. So now this aluminium atom can attain an electronic configuration of noble gas. That means now this aluminium atom is having 8 electrons. Similarly, from this chlorine atom, it can donate a pair of electrons to this AlCl3 unit. So now this aluminium atom is having 8 electrons around it and attains noble gas configuration. So in Al2Cl6 there are 2 Cl-Al coordinate bonds. Cl-Al coordinate bonds. You can see there are only 2 electron pairs in coordinated chlorine atom. All other chlorine atoms are having 3 electron pairs. So it attains a dimeric structure, and it is you can see around aluminium atom there are 4 chlorine atoms. So it is having a distorted tetrahedral arrangement. Now it assumes a state of sp3 hybridization. This is a structure of aluminium chloride dimer, Al2Cl6 dimer. This aluminium chloride attains dimer structure only when it is in the vapor state around 400 degrees Celsius and also in a solution in non-polar solvents like benzene. However, as evidenced from vapor density measurements, aluminum chloride has a monomeric trigonal planar structure about 800 degrees Celsius and accesses discrete LCl3 molecules. This can be explained as resulting from sp2 hybridization undergone by aluminum in AlCl3. So, in the case of when temperature is about 800 degrees Celsius, aluminum chloride can assume a trigonal planar structure and is having discrete LCl3 molecule structure. Means it will access single molecules of, discrete means single molecules of LCl3 unit. It cannot access dimer. That means at a high temperature molecules will dissociate. So we know that at 400 degrees Celsius it can access dimer, but at around 800 degrees Celsius it will dissociate and cannot access dimers, and it will appear as discrete or single LCl3 molecule and is having a trigonal planar structure, monomeric trigonal planar structure. So this is about hybridization is sp2. In the case of temperature above around 400 degrees Celsius, it is having as hybridization of sp3. Now around 800 degrees Celsius, it is having a configuration of sp2 hybridization. It is having a hybridization of aluminum is having hybridization of sp2 and also accesses trigonal planar structure in the form of trigonal planar structure. So this is about the structure of aluminum chloride. There are two types of structures for aluminum chloride. Aluminum chloride can access dimer at around temperature 400 degrees Celsius, and also when we use non-polar solvents like benzene, and it is having a electronic configuration of sp3. And at temperature about 800 degrees Celsius, that means at a high temperature it can access the discrete aluminum chloride molecules and having monomeric trigonal planar structure and is having sp2 hybridization. Now let us discuss another topic, a comparison of the Lewis acidity of boron halides. Boron halides are having the property of Lewis acidity. Lewis acidity means the tendency to accept a pair of electrons. Lewis basicity means tendency to donate a pair of electrons. So let us compare the Lewis acidity of boron halides, which can accept a pair of electrons at higher rate. Reason for the Lewis acidity of boron trihalides. Boron is having an electronic configuration He2s2 That means helium is having 2 electrons. So altogether there are 5 electrons. Then halogen, which may be boron, bromine. This may be bromine. Not boron. Bromine, chlorine, fluorine, and or any halogen. It is having electronic configuration of neon, Ns2, Np5. This neon is having 10 electrons, so altogether there are 17 electrons. In boron trihalides, the boron atom is in a state of sp2 hybridization. As a result, the molecules have trigonal planar geometries. So boron in the ground state, it is having 2s2 2p1 configuration, but in the excited state it is having 1 electrons from s will go to the will get excited to the p orbital. So it will have a configuration of configuration will change into this, that means 2s1 2p2. So this s and p orbital, 2 p orbitals will hybridize together and forming 3 sp2 hybridized orbitals. So there are 3 sp2 hybridized orbitals around boron atom, which can form covalent bond with 3 halogen atoms. That means in halogen there is one unpaired electron in p orbitals that can form covalent bond with a boron atom. So there are 6 electrons around this boron atom. So this is considered as an electron deficient species, and it can accept a pair of electrons and attain noble gas configuration of 8 electrons. So boron has only a sextet of valence electrons around it in such a molecule. Boron would obviously like to complete an octet. Consequently, the boron trihalides are electron deficient compounds having a tendency to accept a pair of electrons from donor. Donor is considered as Lewis base and behave as Lewis acids. So the three bonds, one bond is having two electrons. So there are 6 electrons around boron atom formed by the sharing of bonds between boron and halogen atom. So it can accept a pair of electrons in order to attain electronic configuration of octet. So it can act as a Lewis acid. Lewis acid means, as we already discussed, it is a compound having the tendency to accept a pair of electrons. So it can now act as a pair of now can act as a Lewis acid in order to attain octet configuration. So it can accept a pair of electrons from Lewis base. Lewis base donates a pair of electrons. So this Lewis acid can accept a pair of electrons from any other Lewis base. So this is considered as an electron deficient species. So BF3 is having a trigonal planar structure and is considered as electron deficient species at the same time and a Lewis acid. So it can accept a pair of electrons from any other Lewis base. Now let us discuss about the order of Lewis acidity of boron trihalides. That means which boron trihalide is having high Lewis acidity. So a consideration exclusively of halogen electronegativity. Fluorine is having high electronegativity compared to other halogens, would lead to a prediction that BF3 would be the strongest Lewis acid among the boron halides. That means if fluorine is having high electronegativity, that leads to the strongest Lewis acidity of boron BF3. That means we know that fluorine is having high electronegativity. So we assume BF3 is having a strongest Lewis acid nature. This expectation arises because in BF3 the boron atom is attached to 3 highly electronegative fluorine atoms. We know that in BF3 there are highly electronegative fluorine atoms. There are 3 highly electronegative fluorine atoms. So fluorine being more electronegative than other halogens would be expected to draw electron density away from the boron most strongly, thereby creating the greatest electron deficiency at boron. That means electronegativity means the tendency to attract the shared pair of electrons. So if fluorine is having high electronegativity, that means this shared pair of electrons between boron and fluorine will attract more towards fluorine because of the high electronegativity of fluorine. So there are three fluorine atoms around boron. So these 3 fluorine atoms will attract the shared pair of electrons towards them. So there will appear an electron deficiency around boron. So because of the greatest electron deficiency, it can accept a pair of electrons from a base. That means it can act as a strong Lewis acid compared to other boron trihalides. In other words, on this basis, that means on the basis of electronegativity, we would expect that Lewis acidity would decrease from BF3 to Bi3. That means we already discussed that fluorine is having high electronegativity. Because of that, boron is having a greatest electron deficiency. So it will act as a strong Lewis acid compared to other boron trihalides. So we expect the Lewis acidity order that would decrease from BF3 to Bi3, but that is not the actual case. However, this is not correct. This is not correct, as is evidenced by the stability order of their adducts with Lewis bases. So when we compare the stability order of boron trihalides with Lewis bases, NR3 is considered as Lewis base. Any amine that means trimethyl NCH3 thrice. R group is for any alkyl group. So when we consider the Lewis acid Lewis base adduct stability order, if BF3 is having high Lewis acidity, it should form a strong adduct with Lewis base NR3, but that is not the case we observed. That means when the stability order of the adducts of Lewis acid, different Lewis acids with Lewis base NR3, when we consider the stability order of different Lewis acids with the Lewis base NR3, it was found that the stability order increases from BF3 to BI3. Actually, we expected that BF3 would have a high stability because it is considered as strongest Lewis acid. So it would form a strong adduct with the Lewis base, but that was not the case. The stability order of boron trihalides with Lewis base decrease in the order from BF3 to BI3. So in other words, the relative Lewis acidity of the boron trihalides is found to increase in the order. So from this it was found that the relative acidity order of boron trihalides is found to increase from BF3 to BI3. So actual expected case was not the real one. Based on the stability order of their adducts with the Lewis base, it was found that BF3 is having lower acidity compared to BI3. BI3 is having strong Lewis acidity compared to BF3. So there may be some other reason for the decreased Lewis acidity of BF3 that we will discuss in the upcoming slides. So we can say that the explanation of the order of the acidity of boron trihalides, the observation of the order of Lewis acidity, that is BF3 is having lower acidity compared to BaCl3, then comes BaBr3, then BI3. BI3 is having high acidity, Lewis acidity compared to BF3. So this is the observed order of Lewis acidity, which is contrary to what is expected from the electronegativities of the halogens concerned, that we already discussed. Based on the electronegativity, we expected high Lewis acidity for BF3 and low Lewis acidity for BI3. But observed Lewis acidity order is in this way. BF3 is having low acidity and BI3 is having high acidity. So the reason we will discuss in the next slides. So now we are going to explain why the variation of Lewis acidity in the reverse order. This has been explained on the basis of the relative tendency of the different halogen atoms to backdonate their non-bonded electron pairs to the vacant p orbitals of the boron atom. In other words, in BX3, a shift of electron density from X, the halogen, to boron can occur through pi overlap between a vacant p orbital of boron and a filled p orbital of X. This is referred to as p-pi back bonding. The back bonding in BF3 is shown here. That means in boron, in BF3, boron is having sp2 hybridization. Boron is having ground state S2 p1 configuration. In the excited state, it is having one electron will go to the p orbital and will have this configuration, and one s and two p orbitals undergo hybridization forming sp2 hybridization, that we already discussed. In the case of fluorine atom, it is having 9 electrons, 1s2, 2s2, 2p5. There is one electron in the outermost shell, unpaired electron. So that one unpaired electron is forming covalent bond with all the sp2 hybridized orbital of boron atom and forming 3 covalent bonds. That means there are 3 sp2 hybridized orbitals around in boron. That means 3 sp2 hybridized orbitals contain 3 electrons that can form a covalent bond with fluorine atom. Fluorine contains 1 unpaired electron, so there are 3 covalent bonds around fluorine atom. But in the case of fluorine, there are non-bonded electron pairs that are present in p orbitals that can back donate to the vacant p orbitals of the boron atom. So in BF3, what happens is that the non-bonded electrons that are present in fluorine atom, non-bonded electrons that are present in p orbitals of fluorine atom can donate to vacant p orbitals of b orbital through p pi back bonding. So from fluorine atom, non-bonded electrons can back donate to vacant p orbitals of bromine atom. So there is greater electron density in boron atom. So electron deficiency will get minimized in boron atom. So that is the reason for lower Lewis acidity of boron atom due to the back bonding, p pi back bonding. Here there is a pi bond formation occurs due to the sideways overlap of 2p overlap of 2p orbitals of fluorine and boron atom. So the reason for lower acidity of boron atom is p pi back bonding. Because of the p pi back bonding, it gets high electron density, so that decreases the electron deficiency of boron. So it cannot act as a better Lewis acid compared to other boron trihalides. So at a particular time, one fluorine atom can donate a pair of electrons to the vacant p orbital of boron atom. So at another time, another fluorine atom will back donate p electrons to vacant p orbital of boron atom. So this leads to a resonance structure of BF3. So this is the equivalent resonance structures resulting from p pi back bonding. So there are three equivalent resonance structures possible for BF3 resulting from p pi back bonding. At a particular time, this fluorine atom back donates non-bonded p electrons to boron. Then at another time, this fluorine back donates electrons to this boron. Then there is another possibility for this fluorine atom to back donate electron pairs to this boron atom through p pi back bonding. So this is the reason for the lower acidity of BF3. Thus usually we expect that because of the presence of the highly electronegative fluorine atom, boron in boron trifluoride is having high electron deficient nature. We expect like that. But because of the p pi back bonding, that effectively decreases the electron accepting power of the electron deficient center boron and thereby causes a decrease in Lewis acidity of the halide. That means we usually expect because of the presence of electronegative fluorine atom, highly electronegative fluorine atom, boron will have a high electron deficient center in BF3. And it can accept a pair of electrons from a Lewis base. So it can act as a Lewis acid. But this is not the actual case because of the p pi back bonding that is present in BF3. There will be a back donation of electrons from fluorine to boron. So this decreases the electron deficiency around the central boron atom. So that causes the decrease in the electron accepting tendency or Lewis acidity of BF3. The most effective p-pi back bonding occurs in BF3 because pi overlap is between the vacant 2p orbital of boron and a filled 2p orbital of fluorine, which have similar size and energies. And also the effective p-pi overlapping occurs in BF3 because they have the overlapping orbitals. That means 2p orbital of boron and filled 2p orbital of fluorine. They are having similar size and energies. The efficiency means effectiveness or the power of the pi overlap is less for BCl3 and still less in BBr3 and the least in Bi3 because in comparison with the boron 2p orbital, the size and energy of the overlapping orbit of the halogen increases from chlorine through bromine to iodine. So that means in the case of chlorine it is having 3p orbital, in the case of bromine it is having 4p, when it comes to iodine it is having a 5p orbitals. So the size and energy of the p orbitals of the halogen will increase from fluorine to iodine. So there is highly efficient overlapping occurs between boron and fluorine only compared to other halogen. So as a result, electron efficiency around boron decreases. So as a result, the electron deficiency at the boron atom increases in the order. BF3 is having lower acidity. Electron deficiency means because of the back donation of the electrons through p-pi back bonding. In the case of boron, it is having high electron density because of p-pi back bonding. So electron deficiency around boron decreases. So BF3 is having lower electron deficiency compared to Bi3. Bi3 is having high electron deficiency. So which is also the relative Lewis acidity order. Higher the electron deficiency order, higher it is having the tendency for accepting a pair of electrons. So it can act as a Lewis acid. So Bi3 is having high Lewis acidity compared to BF3 because of the lower p-pi back bonding tendency in lower p-pi back bonding tendency in Bi3 compared to BF3. This is the reason for the Lewis acidity order. Usually we expect high Lewis acidity for BF3 because of the high electronegativity of fluorine, but because of the p-pi back bonding that is present in the boron trihalides, and because of the most effective p-pi back bonding that is present in BF3, it will act as a weak Lewis acid compared to other halides, and Bi3 is having high Lewis acidity because of weak p-pi. Bi3 is having high Lewis acidity because of weak p-pi back bonding due to the large size of the iodine 5p orbitals compared to the 2p orbital of boron atom. So this is about the Lewis acidity order of boron trihalides. Thank you.